Hi, Alex. Good morning. Welcome back. Good morning, Philip. Welcome back. You're doing well. All right, let's get rolling. Good morning. Welcome back. I hope you guys are doing well and staying safe. And I hope you had a good long weekend. Well, seems like a while since I've seen you guys back in the classroom. A little bit more information about acids and bases. Hey, Bellman, welcome back. Hope everything's going okay. I'm looking for a couple people. Looking for Leonardo. I'm looking for Micaiah. If you're here, please let me know. Leo and Micaiah, if you're here, please let me know. All right. First things first, a couple announcements. If you're in 11th grade and you want to go to prom or plan to go to prom, there's some information on your Google Classroom page, your class page, regarding prom. There's a survey on there. Please fill that out if you're interested or want information regarding prom. Seniors, if you have a brother or sister that's a senior, if they don't have this information, you're hearing it from me, you can relate it to them. Seniors, there's information on your grade level Google Classroom regarding graduation. Please fill that out as well. Cap and gowns are $47. So they have to pay for that for graduation too. And last announcement regarding return. If you want to return back to school, whatever level you're in, obviously for sophomores and freshmen, if you want to return back to school, you can return back to school on Monday, May 3rd. And you could just return back to school that way. So you can return back, hopefully filled out the survey. If you're filled it out for virtual and plan to come back in person, maybe you have to reach out to AP just to let them know, hey, I'm going to come back, I'm going to try it out. But the cool thing about this is you have the flexibility. If you want to try it out one day, you don't like the routine, you could continue to learn virtually. It's up to you. So you have that choice. My routine in this class, unless I have over 3/4 of the population, my routine in class will be the same. So I'll do the same teaching. You'll get a Chromebook in my classroom. We'll go through routine. My Chromebook, my computer is actually attached to the smart TV. And it's like a bigger image. Or when you get to class, you could log into the Zoom. I'll let you into the Zoom session. And then you'll have that screen very similar to what you're having at home as well. So I guess the only difference between in-person learning for my class and virtual learning is actually I did print out the guided notes. If you want a hard copy of the guided notes and you want to complete it with a paper and pencil, you have that ability too. So that's like the major difference there. And another thing, I do go through some examples, exit pass questions, a little bit more with the people in front of me in person. Right now, there are 2 people here in class. I don't expect this classroom to be full. I expect probably some of you guys are going to stay home. Some of you guys are going to probably try it out. But once you come to school next Monday, what's going to happen? I know there's a lot of 10th graders here. Is we'll spread out. You're not going to be sitting like right on top of each other. I'm just going to spread you out throughout the classroom, just so you're like not breathing down your classmates' back or anywhere. You do have to wear a mask. I'll wear a mask once you're in class, and we'll follow that routine. If you have any questions, please feel free to ask. Throw in the chat. If you have questions, I'll try to address them. But you will follow your same schedule when you return. You will have the ability to get a locker when you return. If you need help with that, once that return happens, I will definitely assist you with that. All right, let's see what's going on with the COVID report for today. Maybe this is going to help you determine whether or not you'll return. Right now, there's 384 active cases of COVID in the county. Great news. We're below 400. Yes. So a few weeks back, we were below 400. Then it got a little crazy. Now we're below 400 again. That's good. 384 active cases of COVID in the county. Resolved cases, 20,560. And there's 416 deaths from COVID in the county. COVID complications that didn't work out. Hospital systems, there's 21 people in the hospital and 3 people in ICU. Pretty steady there with those numbers. And vaccine numbers, you can check them out. Vaccines are increasing percentage-wise daily. Right now in the county, there's 50.8% of people that are above 16 years old. So almost half the population that are above 16 got their first dose of the vaccine. Cool. More and more people are getting vaccinated. For fully vaccinated, 40%, 40.4% have been fully vaccinated. If you're above 16 and want to get vaccinated, you have the ability to check out the United County website for different pods, different locations of where to get vaccinated. I'm not telling you you have to get vaccinated. I'm just telling you that if you want to, you're above 16, you have the ability to right here. What happens, a lot of pods get set up at different locations around the community just to make it a little bit more convenient for you as well. All right, check out the daily numbers. Let's see what's happening. The daily numbers for today. Sounds like a lottery. Daily numbers for today, last few days, the 25th, there's 16 cases. That's good. A lot lower than maybe that 50 from last week. So 16 on the 25th. Day before that, there's 30. Day before that was 19. Day before that was, looks like 45. So the last few days worth of data, we're heading in the right direction. Definitely looks good. Hopefully we are smart, safe. Know that COVID's definitely still out in the community. Protect yourself, protect your loved ones, wear a mask, social distance, all that good stuff that we've been talking about for over a year. All right, let's figure out what's happening for the best class of the day. Here we go. Welcome back. Seems like forever since I've seen you guys. Welcome back. Quote of the week comes from an unknown source. Life is like a camera. Just focus on what's important. Capture the good times. Develop from the negatives. If things don't work out, take another shot. I like that quote. Life's like a camera. Focus on the important things in life. Take time, capture the good times. Develop from the negatives. Learn from the mistakes. If they don't work out, get up, try it again. Today's Tuesday, April 27th, 2021. It's a day 4. We are going to talk about unit number 9, which is acid, bases, and salts. We will go through topic number 2, Bronsted-Lowry acid bases today in class. We'll start with a YouTube flick. We'll go through some guided notes. We'll watch a second YouTube video on acid bases. And then I'll give you time. We'll go through examples. And then I'll give you time at the end to work on the exit pass. We will go through all this today. Below are the attachments. You have the reference table. You have the 2 flicks in case you want to rewatch them at a later date. So here we go. Let's figure out where we were in class last time. Let me pull up my guided notes. Last time in class, a little refresher, it's been a while, we went through Arrhenius acids and Arrhenius bases. So here we went through the first topic, done. You did the exit pass on Arrhenius acid bases. Hopefully that's completed. Today we're going to go through topic number 2, Bronsted-Lowry acid base theory. So we went through Arrhenius. We talked about Arrhenius. We said Arrhenius has acid is going to be H plus ion or hydronium ion. Arrhenius base is going to be a hydroxide ion, OH negative. So you have H plus versus an H negative. Hopefully we could differentiate between an acid and a base. Again, you did an exit pass related to that. Today we're going through Bronsted-Lowry acid-base theory. Before I jump into the notes, let's play a flick on acids and bases. Bronsted-Lowry theory. Here we go.
The Arrhenius theory of acids and bases defines an acid releases protons in solution and a base as a that releases hydroxide ions in solution. We know that ammonia can act as a base and exhibits alkaline properties, but contains no hydroxide ions. How is this possible? In this lesson, we will learn about the Bronsted-Lowry theory of acids and bases, which fills in the gaps in the Arrhenius theory. You have learned that acids are substances with a pH lower than 7. We can test for acids using universal indicator solution, or paper, which turns red or orange, all depending on the strength of the acid. Blue litmus paper also turns red in the presence of an acid. An example of an acid that you are likely familiar with is hydrochloric acid. Hydrogen chloride dissolves in water to give hydrochloric acid. Hydrogen chloride will dissociate to give a proton and a chloride ion. The proton is not just released, but it is transferred to another substance. For our example, water accepts the proton to form a hydronium ion. A hydronium ion is also known as an oxonium ion. A Bronsted-Lowry acid is a substance that releases or donates protons in solution, in our case, hydrogen chloride. A Bronsted-Lowry base is a substance that accepts protons in solutions, in our case, water. Notice that the definition of a Bronsted-Lowry acid or base is not a function of pH. So an acid-base reaction, according to the Bronsted-Lowry theory, involves the transfer of a proton from one substance to another. In the introduction, we mentioned that ammonia acts as a base even though it does not release hydroxide ions, which is stipulated in the Arrhenius theory. When ammonia dissolves in water, it accepts a proton from water. Notice that this reaction also involves a proton transfer. Can you figure out which substance is acting as an acid in this example? Which is acting as a base? Please pause the lesson to think about this and resume when you are ready.
Let's talk about this for a second. Let's think about this chemical reaction. All right, so we have NH3 gas plus water yields NH4 positive plus OH negative. Figure out this problem. We'll analyze this one. The first thing I would do is mark up NH3. So NH3, let's analyze that. I'll draw a box around it. And the first thing I would ask you guys is say, hey, which compound in the chemical reaction is most similar to NH3? H2O, no, it's quite a bit different. NH4 is definitely most similar to NH3. Those two red boxes are definitely similar. Next up, let's analyze the other two that are similar. H2O is most similar with OH negative. I think you guys can figure out those are pretty similar to each other as well. So again, similarities. Those two are connected. They're similar to each other. And also water and OH. They're pretty darn similar to each other too. Let's go a little further. Let's analyze something. Let's analyze NH3. What's going on from NH3 to NH4? If I ask that question, I know you could figure it out. NH3 to NH4, the difference is the one to the right has an extra H. There's 4 H's on the right one. There's 3 on the left. There's a difference of 1 H, 1 hydrogen. All right. So from reactant to product, NH3 has 3 H's. The product side, NH4, has an extra H. That's the difference. So as we go through the forward reaction, what's going to happen? NH3 is going to gain an H. Where does it get it from? It's going to have to get it from this H2O. H2O, water is going to have to donate an H. NH3 is going to accept an H. Hopefully you can see this transition. My arrow is going to donate an H, and the left one is going to accept an H. except the hydrogen, not a G or a dash. You can see that transition. So NH3 now gains one NH4. Think about water. Let's look at water for a second. Water, H2O, is now going to turn into HO. So we lost one. This can now turn to HO. Let's look at over here. This is, oh, it's in different order, but not a big deal. There's one O, there's one H. One H, one O. So that works out in this situation. So we're really focusing on H's. Which one's going to donate? Which one's going to accept an H for Bronsted-Lowry theory? Let's wrap up the rest of this video.
In this example, water acts as a Bronsted-Lowry acid because it releases a proton. Ammonia acts as a Bronsted-Lowry base because it accepts a proton. So a base, according to the Bronsted-Lowry theory, does not need to have a pH greater than 7, or turn red litmus paper blue, or turn universal indicator solution or paper blue or purple. The only requirement is that it is able to accept protons. Have you noticed that water acted as a base in our first example, but as an acid in the second example? Substances that can act as either an acid or a base. In conclusion, according to the Bronsted-Lowry theory, to release or donate protons. A Bronsted-Lowry base is a substance that accepts protons. Therefore, an acid-base reaction, according to this theory, involves the transfer of a proton.
All right, there's a little intro to acid bases with Bronsted-Lowry theory. Let's put it to paper. Please open up your guided notes. Let's analyze what's going on with Bronsted-Lowry acids and bases. So please open up your guided notes. Let's figure out what's going on with this theory. So a little heads up, what's happening with acid-base unit? There's 3 different topics regarding 3 different theories for acids and bases. Topic number 1, other side. Topic 1 is Arrhenius. Boom, we already went through that. Topic 2 is Bronsted-Lowry. Topic 3 is going to be Lewis, which we'll talk about next time. So the second theory for acids and bases is Bronsted-Lowry theory. In this theory, the Bronsted-Lowry theory, I will highlight, I will bold, I will cap lock. Should give you more time to copy your notes down. So Bronsted-Lowry theory defines an acid as one characteristic and a base as a different. Defines an acid as a hydrogen ion donor. So hydrogen ion donor. So it's going to give off the H, donates its H. And a base, oops, we change that blue. The base is going to be the hydrogen ion acceptor. So one's going to donate an H, one is going to accept an H. Like a redox reaction, something loses electrons, something's going to have to gain the electrons. That's huge. That's going to be the theory that we're going to have to apply at the end of this topic or think about throughout this topic. Once you have that, we're going to represent the example in this text below. This is going to take a couple minutes. Let's analyze the example of ammonia. Once you're ready, please click in the text or the cell below. The equation, I'm going to blow it up really quick, make it a little bit larger. The equation is going to be NH3, oops, NH3, and this is going to be aqueous mixture. Aqueous means a homogeneous mixture. It's probably mixed with water. NH3 plus water, that's going to be liquid. yields at equilibrium. So I'm looking for an equilibrium symbol. Equilibrium symbol, what's going to be? It's going to be insert equations or special characteristics. Sorry, special characters. So again, insert special characters, and then we could draw the symbol over the little drawing pad. Equilibrium symbol is going to be the forward reaction, happens at the same rate as the reverse reaction. This is a cool little feature. You could draw a symbol that it should look like. Is that it? No, not lips. But there's a function for that. U plus 1 F5 E2. Wow, that's crazy. We're looking for equilibrium symbol. If you draw it in, it could pop it in and generate something that's similar to it. Click on it, and it should pop right into the notes. I like that symbol. So again, that means the forward reaction is equal to the reverse reaction. Yields NH4. Charge is going to be a negative. This is going to be aqueous. Plus OH negative as a product. This is going to be aqueous as well. So please try your best to copy that formula. Oh, thank you. This should be 4. Appreciate it. 4. That should be a 4 there. Thank you. Sorry about that. That is a typo there. So it should be NH4. Hopefully it's at NH4. Thanks, Kai. So NH3 plus H2O yields NH4 negative plus OH. Again, please try your best to copy this formula down. I'm going to change the phases just to italic. They're typically going to be italicized. It's not a big deal. Next up, we're really going to mark this whole equation up. We'll figure out which one's donating electrons, which one's donating the H, which one's gaining the H. We'll figure out which one's the acid, which one's going to be the base. Next up, I'm asked that you highlight this entire equation, copy it, Control C, highlight it, copy it, go to the drawing pad, go to Insert, Drawing, New. I'm going to paste it right on here just so I can mark it up a little bit more in detail. My text box is kind of cramped. I'm going to stretch it on out. I want the equation one line right across. Let's do what I did in the video. The first thing I did was look at the first compound. I highlighted it. So I'm going to take a text box or maybe a rectangle here. Let's take a rectangle. I'm going to take a rectangle. I'm going to make it the shape of that compound. I'm going to make it transparent. So instead of filling it in, I'm going to go to transparent. And I'm going to color the box a different color. I don't want it black. I'll make it blue here. Last but not least, I'll make this a thicker box as well. So we have NH3. And then I would ask you guys to say, hey, what's most similar to NH3? Not water. Oh, NH4, it's pretty darn close to NH3. So I'm going to click on this text box. I'm going to go to copy it by hitting Control C. And I'm going to paste the same text box in again so I don't have to change the color, all that stuff right there. So by hitting Control V. Copy that text box, bring it on over, copy, paste, boom. Those two are most similar. They're called a pair, which we'll talk about a little bit later. The H2O is most similar to the OH. I'm going to do the same thing I just did there. I'm going to copy a text box. I'm going to paste it in. I'm going to put it over my water. I'll make it a little bit smaller, and I'm going to change the color this time. So H2O is most similar, make this red, to OH. You could see the similarities right there. Again, it doesn't have to look exactly like mine. Yours could be different. I'm really enjoying these colors because now you could like make yours a little bit more organized, your notes more organized. Typically, if we were in class, I'd say, hey, try to bring like a blue pen, try to bring a red pen to class so we can mark up our notes a little bit. If you don't have them, it's not a big deal. I'm going to take this red box, I'm going to copy, I'm going to paste it. And water is most similar to OH negative. You could see the similarities there. They're pretty close. If anybody needs anything repeated, please ask. But by now, it's like fourth quarter. You guys are like pros with Google Docs. You probably could make images quicker, better than I could. I'm an old man. You guys grew up on technology. All right, next up, I'm going to make another connection here. I'm going to make a little bracket from NH3 to NH4. How do I do that? I'm going to go to selected lines. Actually, shapes. I'm going to go to shapes. I'm going to go to equations. I'm going to go to a left bracket. So here's my trick. Make a bracket. Make a bracket. Just start off with a left bracket. I don't care how big it is. I'm going to take that bracket. I'm going to rotate it 90 degrees to the right, to a 90-degree angle. I'm going to grab that bracket. I'm going to connect it from NH3 to NH4. So now I'm going to expand my bracket right over NH4. Those two are connected. You can see they're very similar to each other. Yeah, you can see with the colors, but Mr. Brown's little cray-cray, there it is. Those two are definitely connected. They're called a Bronsted-Lowry pair. No big deal. We'll talk about it later too. Take another bracket. I'm going to take another equation. I'm going to take another bracket, left bracket again. I'm going to make it, stretch it, release. I'm going to rotate it to the left, whoop, to 270 degrees. And then I'm going to connect my H2O and OH. I'm going to thicken it up as well. You can see that those two are connected again. All right, now let's analyze some of this. So this portion you don't have to draw in here. I'm going to draw from my Zoom annotate screen. I'll do an orange font. So in my next question, after you figured out which two are paired up together, I would have said, hey, what's going on from NH3 to NH4? I'd ask that question. What's going on from NH3 to NH4? Or what's the difference between NH3 to NH4? And then you could easily tell me that the difference is the H's. So again, you don't have to put this portion in here. The NH3 on the left to NH4, there's one more H. You can see that. Where does the H come from? It has to come from the reactant side of the equation. So the H has to come from the reactant side of the equation. It has to come from the only other place where there's an H has to come from the water, H2O. So in this situation, you can see that H2O is donating or releasing the H, and NH3 is going to have to gain the H. Let's think about that process. If I donate an H from water and I gain it from NH3, what happens? It's going to be now NH4, which happens to be right there. That works out. If I donated an H from H2O and lost one, it's now going to be HO. Oh, it's right there. Oh, huh? Oh, it's right there. It's in different order, but there's still a 1-to-1 ratio. That seems like it works out too. So now we can figure out which one donated, which one loses the H. Donated and accepted the H. Let's write that in here. So I'm going to add another text box below. Below the text box of NH3, I'm going to put a text box in. And this is going to be my H plus acceptor. H plus acceptor. accepts the H. H plus acceptor. Gains the H. Accepts it. H plus acceptor. From our notes, from the first thing in notes that we just put in there, the one that takes in the H is going to be the base. I'm adding another text box below. We figured out which one takes in the H. This is going to be the base. It's all about the base, Old song, Mr. Brown. That is a base. And the H2O, we know it lost the H. That's going to be H plus donator. So H plus donator. Oops. Just about. Just. Oh no. It's getting crazy on me, folks. Come on. Let's see. I have to refresh my screen. Oh, there it is. All right, we're okay. Sometimes I get nervous here. H2O, made a text box. This is my H plus donor. H plus donor. Acids are typically red. Bases I will have blue throughout the entire unit. Acids and bases. So again, Bronsted-Lowry theory is focusing on H's. The H plus. Is it donating an H? Is it accepting the H? Make this red. Oh, I made blue. And this is going to be my Bronsted-Lowry acid. So you're thinking about Arrhenius, last theory we just talked about. We said hydronium H plus was the acid, and we said OH negative was the base. Bronsted-Lowry theory is a little bit different. One's donating an H, one's accepting an H. So now we just figured out what's the acid and base by just looking at donating and accepting an H. Let's look at the reverse reaction. So this is for the forward reaction, NH3, 10H4. Let's look at the second portion. Let's look at the reverse reaction of this equation. So let's check out what happens when we go from product to the reactant. So this portion of the arrow. Let's see what happens there. So now let's look at the reverse reaction from NH3 to NH4 to NH3. What happens there? So NH4 to NH3, you know what happens. From NH4 to NH3, we lost an H. So think about this process. We lost an H. An H is going to have to be donated to the other thing in the product side, to OH. This reverse reaction, NH4 donates an H, and OH accepts the H. Now we can figure out the reverse reaction for Bronsted-Lowry acid and bases. Let's do this. So here we go. I'm going to copy and paste these two text boxes above. I'm going to copy somehow. I think I could. So I could right-click my mouse, copy both those text boxes, hit Control-C, hit Control-V, paste it. Now I'm going to use my keypad. I'm just going to scroll on over. Hopefully you remembered what happened there. NH4 in the reverse reaction is going to be the donor. It donated the H. Do the same thing for the base. Right-click your mouse, highlight both text boxes, copy, paste, use your arrows, bring it all the way over to OH. that OH negative would be the base in the reverse reaction. That's the image that I wanted to create here. If you do want to represent the forward reaction with some arrows, you can. You don't have to. Forward reaction, we could say, hey, we lost an H. It's going to be tough for me. Maybe you wanted to represent it. Maybe you don't want to. I guess I'll try to do it with orange font. I don't know. So you can see the transition in the forward reaction. Oops, wrong way. So if you want to represent the arrows from H2O to NH3, you can. I'm not going to. I didn't like the way that looked. I couldn't get an arched arrow. Could scribble it. Whoop. Kind of. I'm not going to. You can save and close that image, please. Please save and close that image. Hopefully that submit saves in the text box. Again, if you have a problem, you can refresh your screen, copy it all, cut it all, Control X, and paste it back in. Click off it, save and close. That usually does the trick. So please open up that image as big as you can, just so it pops up in the notes. And the next portion of notes is referring to this. So here we go. We're talking about production of ammonia. We talked about one accepting an H, donating an H. In this reaction, you could see that ammonia, which is going to be NH3, it's a polyatomic ion. It's on page 2 of the reference table if you need to refer to that. Ammonia is going to be the hydrogen ion acceptor. Ammonia is a hydrogen ion acceptor. Therefore, it's going to be the Bronsted-Lowry base. This situation, water is going to be the hydrogen ion donor. The example above, water is a hydrogen ion donor, and therefore is a Bronsted-Lowry acid, which is given to you. I'm going to highlight it red just so you know what it's referring to above. You're trying to figure out an acid, you're trying to figure out a base, please take the same approach that we just did there. Figure out which two are connected, which two are paired up together, and then you can figure out which one's donating an H, which one's accepting an H. We'll analyze some examples a little bit later. Moving forward, a conjugate acid base. A conjugate acid base pairs. So conjugate acid base pairs. Conjugate acid base pairs. Oops. Hold up here. Conjugate acid, not base pairs. Conjugate acid is a particle formed when the base, that's a typo there. Conjugate acid is a particle formed when a base gains a hydrogen ion. particle formed when a base gains a hydrogen ion. So it's gaining an H. Conjugate acid comes from the base. Particle formed when a base gains a hydrogen ion. Look at the example above. Conjugate acid. Base gains a hydrogen ion. Oh, there's my base. It gains a hydrogen ion. Just gains it. The other blue one would be the conjugate acid. So this would actually be conjugate acid. The acid is going to be particle formed when it donates a hydrogen ion. So this would be the conjugate base. So conjugate means joint. Which ones are joined together? The conjugate base is a particle formed when an acid has donated. Acid has donated a hydrogen ion. H ion, hydrogen ion. So opposites again. Conjugate base, what is it? It's the acid. Conjugate acid bases are paired with a base or an acid, respectively. And we will go through an example with conjugate acid, conjugate bases. They're paired with an acid or a base, respectively. So think of conjugate being opposites. Hey, how you doing? Jam? All right, sorry about that. All right, so conjugate acid-base pairs with an acid or a base, respectively. So it's going to be paired up with both. Acid-base pairs. Here we go. Conjugate acid-base pairs. Base. They consist of two substances. Conjugate acid-base pairs consist of two. All right, sorry about that, folks. Conjugate acid-base pairs, they consist of two substances related by a loss or gain of hydrogen. So hydrogen ions, definitely important here. We already went through that process. We talked about which one's an acid, we talked about which one's a base. We made the two rectangles, which were similar. Whatever two color rectangles were the same were the acid-base pair. They're paired up together. All right, before I go to the next portion of notes, I will play a flick regarding conjugate acid-base pairs. So if you need more time in the notes, you have it. Let's watch this flick regarding conjugate acid bases.
We have previously learned about the Bronsted-Lowry theory of acids and bases. We will now learn about conjugate acids and bases using our knowledge of the Bronsted-Lowry theory. Let's do a quick warm-up. Vinegar is a 5% aqueous solution of acetic acid. Vinegar is used in cooking worldwide and is sometimes used as a cleaning agent. From the equation, which describes the behavior of acetic acid in water, could you identify the Bronsted-Lowry acid and the Bronsted-Lowry base? Pause and resume when ready.
Let's check it out. Could we identify the Bronsted-Lowry acid and the Bronsted-Lowry base? First thing I would do, put the boxes in or highlight the portions. All right, we have CH3COOH. I would say, hey, which one's most similar to that? You'd say, oh, CH3COO negative. They're very similar. You do the same thing for the next compound, water. H2O is most similar to H3O. Then you're like, oh, which one's donating an H? Which one's gaining an H? This is a Ford reaction. So we're analyzing the Ford reaction. My next question for you would be like, what happens from CH3COOH to CH3COO? So I'd say, hey, analyze that. What's going on from this to this? What's the difference? You can see the difference. Over here is missing an H. It's one less H there in that situation. So think about that process. How do we have one less H? You're going to have to donate. H is going to be donated to the H2O. So you have one donating. So again, situation, you can see that this is donating. You can see that H2O is going to accept the H. Donor acceptor, the one that accepts the H, looks like it's going to be a base. Nice, Tristan, thank you. The one that donates is going to be the acid. So you should be able to figure out that process. You should be able to label acid bases for Bronsted-Lowry theory. Let's see.
The Bronsted-Lowry acid is acetic acid because it releases a proton. Water accepted a proton from acetic acid, so it is a Bronsted-Lowry base. As we have learned, an acid-base reaction, all according to the Bronsted-Lowry theory, involves the transfer of a proton. Let's now look at what has been formed from this reaction. The acetate ion is formed when acetic acid released a proton. The acetate ion is the conjugate base in this reaction. Can you remember what this is called? Pause and resume when ready. This is a hydronium ion, also known as an oxonium ion. The hydronium ion is formed when water accepted a proton from acetic acid. This is the conjugate acid in this reaction. When a Bronsted-Lowry acid releases a proton, the resulting species is its conjugate base. When a Bronsted-Lowry base accepts a proton, the resulting species is its conjugate acid. Acetic acid and the acetate ion is a conjugate pair. Can you identify the other conjugate pair in this reaction? Pause and resume when ready. Water and the hydronium ion is the other conjugate pair. So an acid and its conjugate base is a conjugate pair, and a base and its conjugate acid is also a conjugate pair. Now, are you ready for a challenge? For this reaction, try to identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate pairs. Let's grab a piece of paper and a pencil, pause the lesson, and resume when ready.
Okay, let's try another example out. Here we go. Let's see if we can do this. Another example for us to analyze. We have H2SO4 plus NH3 yields HSO4 plus NH4. Think about this process. Figure out which two are most similar to each other. Here you go. You know my process. There's my box. H2SO4 is most similar to HSO4. The other box, let's mark it up. NH3 is most similar to NH4. All right, so the two red boxes are paired up together. They're going to be a pair. So two red boxes would be a pair. The two blue boxes would be a pair too. So this is one pair. And the other pair is going to be HSO4 and H2SO4 and HSO4. They're a pair as well. So two red boxes are a pair, two blue boxes are a pair. Okay, we could do that. Now we have to figure out which one's the acid, which one's the base. Let's analyze the two red boxes in the forward reaction. So H2SO4 to HSO4, what's the difference there? You can analyze that and say, oh, there's two H's there. There's one H there. The difference is we're missing an H on the right. So what's going to have to happen? We're going to have to take one of these H's. We're going to have to donate an H to the NH3. You should be able to think about this process. We are donating an H donor. H donor is going to have to be your acid. To the right, what's happening here? We are accepting H acceptor. Taking in. This is going to have to be your base. So that's going to be your base. Conjugate acid bases. Follow the little pairs. All right. Do a different color. I'll use brown now. There's an acid, Bronsted-Lowry acid, on a brown. There's a Bronsted-Lowry acid. The other side is going to have to be the conjugate base, CB. Here's my Bronsted-Lowry base. This would have to be my conjugate acid. Opposites in that situation. Let's see how we did.
The Bronsted-Lowry acid is sulfuric acid as it releases a proton to ammonia. Since ammonia accepted the proton, it is the Bronsted-Lowry base. The hydrogen sulfate ion is the conjugate base of sulfuric acid. The ammonium ion is the conjugate acid of ammonia. Therefore, sulfuric acid and the hydrogen sulfate ion form a conjugate pair, and ammonia and the ammonium ion form another conjugate pair. In summary, a conjugate base is formed when a Bronsted-Lowry acid releases its proton, and a conjugate acid is formed when a Bronsted-Lowry base accepts a proton. A Bronsted-Lowry acid and its conjugate base is a conjugate pair, as is a Bronsted-Lowry base and its conjugate acid.
All right, so there's some information on conjugate acid and bases. Let's get back to notes. Picking off where we left off, another example. Let's identify conjugate acid-base pairs. So for this example, I'm going to take the exact same equation I have above. I'm going to copy and paste it, and I'm going to modify the equation a little bit. So please take this equation that we already generated, that we already highlighted, click on it. There should be a blue box around it. I'm going to copy it, and I'm going to paste it within the same text box. Or the text box below, not the same text box. Do want to analyze this equation right there again. So I do want to leave, I'll leave the base, I'll leave H plus acceptor, leave acid, H plus donor, but I do want to label the other side of the equation differently. So I'm going to double click on this image. edit this image. And we're going to modify this. Instead of doing H plus donor over here or acid, we're going to change that to conjugate acid. So in this situation, I'm going to get rid of this and call this conjugate acid. Conjugate acid. And we have a conjugate base. Conjugate acid, conjugate base. Again, notice the comparisons. The base, the Bronsted-Lowry base, is the conjugate acid. The Bronsted-Lowry acid is the conjugate base. They're opposites. Last thing I want to put here are the acid-base pairs. Above the brackets, I'm going to put a text box. And I'm going to put conjugate acid-base pairs. Conjugate acid-base pairs. I'll go purple here so you can make those comparisons. Those are the conjugate acid-base pairs. They're paired up together. That's an easy question. Below, these are going to be the conjugate acid-base pairs. The two red boxes are conjugate acid-base pairs as well. So two red boxes, I guess I'll keep this red font. Copy this text box, paste it below. These are my conjugate acid-base pairs. Paired up together. It's going to look like a lot of red, but I'm going with it. Okay, that is the image that I wanted you to create. Hopefully you did that. Once you have that image, please save it and close it. Sometimes it works, sometimes it doesn't. Nice. Conjugate acid-base pairs. In this situation here, we have the ammonia molecule and ammonium ion being the conjugate acid-base pairs. We labeled it. So again, the two blue boxes, we have ammonia, NH3, and ammonia ion, NH4. They're paired up together. The water molecule and the hydroxide ion are going to be the acid-base pairs as well. You can see that. Okay, let's take it a step further. Some conjugate acid-base pairs. So common conjugate acid-base pairs. Please go to the next page. I'm on page 5 now. There are several acid-base pairs. In this situation, acids, I'm just going to highlight this quick. Keep my acids in red. Keep my bases in blue. I'm going to take the paint can, actually, and just paint it all. Pairs. Several pairs that we could have. HCl. HCl turns to base of Cl. Think about the process. HCl to Cl. The acid's going to donate. The base would accept. So once you donate an H, it's turns into Cl. Next one, H2SO4. H2SO4 turns into HSO4. HSO4. Charge would be a negative. HSO4 negative. HSO4 negative would turn into a conjugate base. I think you probably know you're going to lose an H, donate an H. Turns into SO4. The acid for CH3COO negative would be CH3. COOH. That's the acid. The base for H2CO3 would be HCO3 negative. The base for water is going to be OH. Base for water would be OH. Charge, negative. Charge would be negative. I'm going to ask that we add one more text box below for one more example. How do you do another text box? Just hit tab. So after the OH negative, press tab and it adds another text box for you. The last one's hydronium, H3O positive. Turns into a base by water, via water. There's another example for Bronsted-Lowry theory. Acid-base pairs. Do you have to memorize these? No. You should be familiar with it from your notes, though. Acids, base, pair. Are they going to test you this on the benchmark exam? No, not going to memorize them. Would they ask you to memorize on the Regents? No. Just good to be familiar with some acid-base pairs. Okay, last but not least for today's class, we're going to represent the acid, represent the base in these text boxes below, and we'll use this to help us with the examples. So acid, base, Bronsted-Lowry acid. By now we should be aware what a Bronsted-Lowry acid is. It's going to be an H plus or proton donor. H plus or proton donor. Bronsted-Lowry base is going to be an H plus or proton acceptor. That is it for the notes for today. Bronsted-Lowry acid bases. Once you're all set with the notes, please open up the examples from the Google Classroom page. We'll go through some examples. Once we're done with that, we'll take the rest of the time to give you to work on the exit passes. You will see very soon that the examples are going to be super simple. These are the types of questions they would have asked in the Regents, maybe on the benchmark exam, maybe on the exit pass, benchmark exam, or post-test. Maybe on post-test you'll have questions very similar to this too. So please open up the examples. We'll do the examples together. Once we're done with that, we'll give you the rest of the time to work on the exit pass. But here we go. Use your notes. They're right there for you. Question number 1, according to Bronsted-Lowry theory, an acid is, use your notes. It's super simple. Acids are H plus or proton donor, not electrons. Acids are proton donor. One, done. Easy. One is A, proton donor. Next up, number 2, according to Bronsted-Lowry theory, an acid, Bronsted-Lowry theory for an acid is a H plus or proton donor. Know this theory, you know this answer. Proton donor only. Not acceptor. It's not either or, and it's not neither. 2, best answer is going to be choice A. Proton donor acid. Number 3, according to the Bronsted-Lowry theory, water is considered a base when's it all about the base? Bronsted-Lowry theory is a base. We did not talk about anything about electrons here. It's not A, it's not B. Yeah, it's going to have to be accepting DH. Accepting DH. Choice D is the best answer for number 3. Told you they're easy question, folks. 3 is D. Easy. Number 4. According to Bronsted-Lowry theory, H2O acts as what? Good. We finally have a tougher question. H2O acts as what? Think about this process. Let's go through and highlight some things here. NH3 is most similar to NH4. Water is most similar to OH negative. Let's analyze the 2 blue boxes. 2 blue boxes, NH3 and NH4. What's the difference? The one to the right has an extra H. Therefore, the one on the left is going to have to gain an H. H2O donates an H. Talking about H2O, it's donating an H. Donor, donating an H, donating a proton. H plus is the same thing as a proton, by the way. Donating a proton. Choice D is definitely the best answer for number 4. 4 is D, donor. Number 5, next up. According to Bronsted-Lowry theory, an acid acts. An acid is any species that, easy, donates a proton to another species. It's got to be choice C. Number 5 is C. Number 6, one acid-base theory states that an acid is, memorize that phrase right there, memorize that little key right there. It's super simple. It's behind me too. I actually put it right here as well. The 3 theories. Acid is an H plus donor. Not H negative, H plus. Choice C is the best answer for number 6. Last question on the examples. Which statement describes an alternate theory of an acid and base? Which one's a theory for an acid and base? Arrhenius talked about hydroxide and hydronium. Hydronium acid, hydroxide base. Another theory talks about an acid being proton donor or H plus donor, a base being an H plus or proton acceptor. Best answer for number 7, acids and bases. Okay. Acid and bases are both? No. One's going to accept, one's going to donate. Both are donors? No. Acids are H plus acceptors? No. Acids are H plus donors. Bases are H plus acceptors. 7, best answer is D. You can submit this. Hopefully you got a 7 out of 7. This is not getting graded. What's going to be graded is the exit pass. Please open up the exit pass for Bronsted-Lowry theory, topic number 2, unit 9. I do want to analyze at least one question here. There's a typo in one of them. Please open up the exit pass for unit 9, Bronsted-Lowry theory, acids and bases. There's 8 questions here. There's plenty of time to do this. 8 questions here. I do want to go through question number 7, I believe it is. Yes. Question number 7. Different question. In the reaction, NH3 plus N2O at equilibrium yields NH4 plus OH negative. A conjugate acid-base pair is what? We're trying to figure out which two are paired up together. This situation, I would make boxes around NH3 and say, what's most similar to NH3? And you're going to say, hey, NH4 is pretty darn close to NH3. Do the same thing for the other compounds. OH is most similar to, it's got to be this thing. But right there, there is a typo. It's not N2O. It should just be water, H2O. So that should be H2O. The 2 red boxes are paired up. That's a conjugate acid-base pair. The 2 blue boxes are paired up together too. Those are a conjugate acid-base pair as well. So answers would be NH3 and NH4. NH3, NH4, no, not right. NH3 and NH4, no, not right. H2O and OH looks like a solid choice. H2O, NH4, no, that's not right. Pairs, the 2 blue boxes, are paired up together. 7, the best answer is choice D. 7, the best answer is D. Okay, you have 7 more questions to complete for the exit pass. I will go through question number 2 since somebody else asked about it. So let's check out number 2. Acid-base theory. Which one's a Bronsted-Lowry acid-base theory? Use this right here. So question number 2 wants to know which one's an alternate acid-base theory. Which statement's an acid-base theory? Acid's gonna have to be a H plus donor. Acid's gotta be H. Oh, it's gotta be H plus. So it's not gonna be choice C. It's not gonna be choice D because it's H negative. It's gotta be H plus. H plus donor. The base is the H plus acceptor. All I did there is use this section right there. Choice B looks like the best answer for choice or question number 2. Hopefully that helps. Use your notes. Okay, what's going to happen from here the rest of the class? There's 10 minutes left. You have plenty of time to do the rest of the exit pass. I'm going to put you in breakout rooms for the last 10 minutes of class. Please complete this exit pass. This is due Saturday. In the event you do not finish it up, I would do it right now. If you have any questions, feel free to ask for help. I'm here to help you out. If you get done early, feel free to leave. That is it for today. Wait. What are we doing for blank ones? Which ones are blank? They should all have answers this time, I believe. Are we doing the right exit pass? Topic 2, Bronsted-Lowry acid bases. They should all have an answer for that one. Huh. Does anybody else have blank answers? Just make sure it's exit pass unit 9, topic 2, Bronsted-Lowry acid-base theory. Maybe refresh your screen, try it out. All right, if you have questions, feel free to ask for help in the breakout room. You're in a breakout room by yourself. You have here to the end of class to finish it up. If you get done early, feel free to leave. Have a good day, guys. We'll see you later. Bye. Please join the breakout room. Please complete the exit pass.